in the last couple of lectures, if you recall, we had talked about the design of adders. We talked about half adders, full adders, then we saw how we can combine them to create parallel adders. Two kinds of parallel adders we have seen so far: ripple carry adder, where the delay increases with the number of bits, and carry lookup adder, where the delay is constant, but the hardware complexity, number of gates, size of gates, they increase very rapidly with the number of bits. So, in practice we need some kind of a trade off. We cannot design a 64-bit carry lookup adder because the gates will become too complex, but we cannot also design a 64-bit ripple carry adder because the delay will have to ripple through all the stages. So, we have to have some kind of compromise. Let us look into it. This is our third part of adder design. So, here I shall not be going into too much detail, just I will try to give you the basic idea in the concept. See, we are trying to design a 16-bit adder, let us say, and suppose we have already designed 4-bit carry lookup adder modules as we had discussed in the last lecture. Suppose we have such 4-bit carry lookup adder modules available with us. So, we can add two 4-bit numbers and generate a 4-bit sum. Now, one thing we can always do, we can cascade these 4-bit lookup adders like this. You see, this 4-bit carry lookup adder, if you recall earlier, that we need 5 delta time to generate the carry and 8 delta time to generate the sum. So, this sum will be generated after time 8 delta, and this carry is being generated here. So, again after some delay this will be generated. So, you can calculate the total time taken. So, there will be a rippling of carry still going on across the 4-bit carry lookup adder stages, but within each of these blocks the time is constant. This is the basic idea. Okay. So, carry propagation between modules are still there. Let us do a simple calculation. So, one thing you can do, we can use a second level of carry lookup mechanism. Like in the previous diagram we said that we have 4-bit carry lookup adder modules, where there will be carry propagation between stages or between these modules. So, what you can do, we can have a higher level carry lookup adder kind of a scheme again, where all these carries can be generated in parallel. So, you do not need to have this carry propagation again. Same concept which you had for carry lookup adder, we are using it in the higher level also to generate C4, C8, C12 and C16. Like if you just go to the previous slide, this C4, C8, C12 and C16. If I have a higher level carry lookup module which can generate these in parallel, then this rippling effect will no longer be required. So, a simple delay calculation I am showing here. Now, this carry lookup adder, as you know, that requires only 2 stages AND and OR, it will require 2 gate delays twice delta. And for a 16-bit adder 4444, for the original single level carry lookup adder, if you do it, it would be 14 delta, but for modified 2 level it will be reduced 10 delta. So, here I am not going into the detail of this, but I am just telling you that if you have a modified 2 level carry lookup adding scheme, the delay can be reduced. So, the basic idea I gave you. So, this table gives a quick comparison that for certain values of n, typical values 416 up to 256 I am showing, if you have a normal ripple carry adder, the total delay will go, if you recall, total delay is 2n plus 1 delta. So, it will go up like this 9, 33, 65 up to 513. But for carry lookup adder it is 444 in term. So, it will grow like that. You build a 4-bit adder, 4 such you build 16, 4 such you build 64, 4 such you get 256 and so on. So, if you make a calculation you will see that the delay are much less. Between 16 and 64 they do not change. So, you see, so above 16 if you go it will become 12 up to 64, and above 64 if you will go it will be 14 up to 250. So, it will increase by 2 each. So, for every power of 2, like you go from 4 to 16 to 64 to 256, your delay increases by 2 each. So, for 4 it is 8 delta, for 16 it is 10 delta, 64 it is 12 delta, and 256 it is 14 delta. And if you have any other value between like 128, that will also be this 14 delta, as you can see. So, 32 for example, 32 is also 12 delta. So, you see the carry lookup adder delay is much less, much less as compared to ripple carry adder. This is one point. Now, let us look at some other kinds of adders. Of course, we shall not be going into too much detail on these. These are a slightly advanced kind of an adder which can generate the sum with an average delay which is much smaller as compared to the conventional adders. Let us see the basic concept. The first kind of adder we talk about is called a carry select adder. Well, carry select adder, the idea is very simple. Let us talk about an addition module. Let us say we have several modules of addition which are cascaded, like we have talked about several 4-bit adders connected in cascade. So, for one stage of a 4-bit adder, the carry is coming from the previous stage and the carry out will be going to the next stage. Let us consider one such stage. Now, in that stage the input carry can be either equal to 0, it can also be equal to 1. So, we do not know what the carry will be at time t equal to 0. We will have to wait for certain time for the carry to get generated, only then we will be knowing what the carry is. Now, the idea is that we have two concurrent versions of the adder. That means, there is two hardware we are using, two adders. One adder is doing addition in advance assuming carry is 0, another adder is doing addition in advance assuming carry is 1, but we do not know what the actual carry is. Okay. So, we carry out addition twice, once with carry as 0, once with carry at 1. Later on, when the previous stage has generated the actual carry, because you see already these two additions have been complete, they have added and is waiting. Now, we can have a multiplexer. This multiplexer can be selected by this actual carry. So, either this will get selected or this will get selected. The correct sum is selected by a multiplexer, right. So, multiplexer, if you recall, multiplexer is any circuit where there are two inputs, there is one output, there is one select line. It will either select this or select this depending on the value of the select line. If S is 0, this will be selected. If S is 1, this will be selected. Okay. Now, I am just showing you how a carry select adder looks like. Consider a 4-bit adder module just like what we saw earlier. So, now we have two parallel 4-bit adders, one is here, one is here. You see one of them is adding assuming carry in is 0, other is adding assuming carry in is 1. Later on, when the carry in actually becomes available from the previous stage, but these full adders have already completed their addition. So, their sums are already available here, their sums are already available here. Okay. So, depending on the actual value of carry in, you either select the topmost adder or the bottommost adder depending on the actual value of carry in, and either this or this will get selected as the final sum. Similarly, the carry, you select either this carry or this carry depending on C in. So, you will be getting the final carry out. So, the idea is this, we are investing on hardware, we are using double the amount of hardware and we are doing some speculation, we are doing an addition both for carry 0 also for carry 1, and we are being ready with the two sums, and once when the carry is available we are selecting one of the two sums using a multiplexer. So, we are avoiding the addition delay, only the multiplexer delay which is much smaller, that will be incurred. Okay. This is the idea. So, this is an example where we have 4-bit modules. Now, the second thing is that if we have a multi such stage addition, the number of full adders in every stage can be either uniform or variable. Let us see. This is an example of a uniform sized adder, where I am saying this is a 16-bit adder, this is stage, first stage, second stage, third stage and fourth stage, 4-bit, 4-bit, 4-bit adder. For the first stage there is no confusion because carry in is directly available. So, you do not need 2 copies of adder, only 1 adder. But for the other stages there are 2 adders and they are adding with carry 0 and carry 1 in parallel. So, once the carry gets available, say for example, the first stage computes this carry will be selecting these S 4, 5, 6 and 7, also it will be selecting the correct carry here, and this correct carry will now be selecting S 8, S 9, S 10, S 11, it will be selecting here and again 12, 13, 14, 15 and C out. So, you see here also there is a rippling effect, but this rippling effect is much faster because this is only through a multiplexer, not through full adders. So, here the total delay of the 16-bit adder will be only 4 full adder delays, because each of these stages are taking 4-bit full adder delays, assuming it is a ripple carry adder. Let us say, assuming ripple carry adder, it will be 4 full adder delays. If it is a carry lookup adder, it will be even faster, plus these 3 multiplexer delays, right. Now, you can also improve upon this using a very intelligent way by using variable sized adders. Variable size means you see you use 2-bit adder, 3-bit adder, 4-bit adder, 5-bit adder, because the input bits you do not divide equally. This is also 2, say this A0, A1, B0, B1, this is also 2, A2, A3, A4, A5, A6, this is 4-bit, this is 5-bit, but ultimately you are getting a 16-bit adder still. See here the advantage is that, see when you the first stage has completed 2-bit addition, let us say, this 2-bit addition is also completed. So, after a 1-bit multiplexer delay you will be getting here. So, this 2 full adder delay plus 1. Now, this adder by this time has finished addition, because assuming 1 full adder delay and 1 mux delay are equal, here the delay was 2 full adder delay plus 1 mux delay. By that time this carry is generated, this full adder is also ready with the sum and the carry. So, you can directly apply it here, and by the time it is ready plus 1 mux delay, this 4-bit adder is also ready, because 3 plus 1 is 4. Similarly, 4 plus 1 mux delay, when that comes here, this is also ready. So, you do not have to wait any more for the later stages, because when the carry comes, the adders are already ready with their sums. So, you need only 2 full adder delays corresponding to the first stage plus the mux delays. So, the delay gets reduced, right. I am not going into too much detail about this, as I told you, just trying to give you an idea. This is sometimes called a 2, 2, 3, 4, 5 configuration, 2, 2, 3, 4 and 5. This is how the number of bits are divided. The last kind of adder that I talk about here is something called a carry save adder. Now, it is a little beyond the scope of this course to talk about the application. It is very useful for the design of multipliers, carry save adders, but we shall not be discussing this here. We shall be telling you what the basic concept of carry save adder is and how you can design it. See, a normal adder adds 2 numbers, right. You have 2 input numbers, you generate sum and carry. But in a carry save adder, you are adding 3 numbers x, y and z. So, you are adding 3 numbers and you are generating a sum and carry. These are not 1 bit numbers, these can be n bit numbers. Now, we shall see how it works, because we are seeing that there are 3 operands, but the carry save adder is nothing but an independent full adder without carry propagation. There is no carry propagation here. Let us try to understand this, what is meant by no carry propagation, and that a parallel adder may be required at the last stage. Let us take an example. Consider an addition. Suppose I have 3 numbers x, y, z which I am adding, because as I said, for a carry save adder we talk about adding 3 numbers. So, we are showing the carry and sum separately. So, when you add x, y, z 1, 1, 1, it is 1 with a carry of 1. Okay, we are not just adding with carry, we are independently adding the different stages. 1, 0, 0 is 0 with a carry of 1, 0, 0, 0 is 0 with a carry of 0, 0, 1, 1 is 0 with a carry of 1 and 1, 1, 0 is 0 with a carry of 1. Now, what I do, you see we have accumulated this sum 0, 0, 0, 0, 1 parallelly without carry propagation, and also carry 1, 1, 0, 0, 1, 1, the carry out from the different stages. We shift the carry by 1 position and add with s. Whatever we get is the actual sum of x, y and z. So, the idea is that we are not doing the conventional kind of addition. Instead of using the carries from one stage to the other, we are actually doing the addition like this. We are doing a parallel addition without carry propagation. We are generating the sum separately, generating the carry separately. A set of full adders, independent full adders, that means each full adder will be like this. There are 3 inputs and just 2 outputs, sum and carry. No carry propagation from one stage to the next. So, this can be done in constant time, and after this constant time, the last stage you need an adder to add s and c after one shift. So, you need an adder of course at the end, but not before that. But why do we need this? What is the advantage? The advantage will be if you have many numbers to add, like n bit carry save adder just looks like this, set of independent n full adders. Each full adder takes 3 bits of the inputs x, y and z and generates carry and sum separately, right. So, let us take some examples. Suppose I have 3 numbers, just like I showed previously, just in the previous one you see there are 3 numbers x, y, z In the output I generate a sum and a carry. So, it is like this. There are 3 numbers m equal to 3. I use one carry save adder, the 3 numbers are applied in the input. So, sum and carry are generated. So, as I said, at the last stage after shifting I need one parallel adder, I get the final sum. Now, for m equal to 3 we do not see any advantage, unnecessary we are doing it complicated, because ultimately we need an adder at the end. The advantage will be apparent if you use some higher value of m. Suppose we are wanting to add 4 numbers. First 3 numbers are applied here, the 4th number is applied here. You see, we use a carry save adder in the first stage, you generate a sum and a carry independent. This sum, carry and the 4th number you feed it to another carry save adder, it will generate a sum and a carry, and finally you apply it to a parallel adder with carry propagation to generate the final result. So, these two CSA and CSA will be requiring constant time without carry propagation, only the last stage will be using carry propagation. Let us say m equal to 6, there are 6 numbers I want to add. See, first stage I use 2 carry save adders. So, 1, 2, 3, 4, 5, 6 I am adding. So, 1 sum and 1 carry, 1 sum and 1 carry. So, I can use another carry save adder to add 2 of this and 1 of these. I have finally 1 sum and 1 carry, and also this 6th one. You see, ultimately we will have to bring it down to 2. That is why we need a tree of such carry save adders. You see, here this parallel adder will take only 2 inputs at the last stage. So, you have 6 down to 4, down to 3, down to 1, we will have a chain of such carry save adders. The advantage is that each carry save adder will be just independent full adders, they will have a delay of 3 delta each, 3 delta, 3 delta, 3 delta. Only at the end there is a rippling of the parallel adder. But the advantage is that you are able to add 6 numbers together, 9 delta plus the delay of 1 parallel adder. This is the main advantage here. But as I mentioned, these are some kind of slightly advanced kind of adders, and we do not need to go into too much detail about this. Just to give you an idea that this kind of carry select and carry save adders are also possible, and they have very interesting applications in some other areas maybe. So, with this we come to the end of this lecture. You see, over the past 3 lectures we basically talked about various kind of adders. Now, in the next few lectures we shall be looking at how we can design other basic combinational circuit modules and how they can be used in certain applications. Logic design is of course one application, we want to realize or implement some function, but there can be other kinds of applications as well. This we shall be discussing in our next lectures. Thank you.